recording this. Okay, so just as an official start to this, my name is Nicholas Crouch. I work for the Maths Learning Centre at the University of Adelaide. The Maths Learning Centre is not associated with the Maths department, which teaches Maths1M. We are part of the same university, and we're here to help all students with mathematics across the university. However, not being part of the university, not being part of the School of Maths, means that I do not know anything about the content. I do not know what is going to be in the exam, and I can only go on what resources you have available to you through my uni as a guide to what's in the course. Having said that, I've talked a lot about doing Maths1M over the years, and so I know a lot about what's going on. So this is your opportunity to talk to me and to ask questions from me. One of the things I will do is I'll go, where did it go? So if we look, this is actually the Maths Learning Centre's webpage for Maths1M. So if we look under Maths, like all of the university, all the Maths Learning Centre sites have this bit along the side. And so if we click on the bit that says resources, all right, there will be a thing across the top which will allow you to, well, let's click on the resources. If I just click there, it'll take us to this page, which has a thing across. And so I've just gone here and then selected 1M. And so you can see we've got various resources for all sorts of things. And you'll see, where did it go? I saw it, revision seminars. There we go. And so if I look at the revision seminars, you can see David's tried to put up a little bit of an indication of what's in each revision seminar for you to look at. So vectors, lines, planes, curves, as well as solving equations with trig functions. So study skills and problem solving skills for maths, especially in preparation for the exam. Visualizing lines and planes in 3 dimensions. So you can see at the top of each one, there's a little bit of information about what's in the course. So what's in that particular revision seminar, and these go back 2018. So there's a couple of things I could do. So one of the things I did is I actually just opened up the course notes. And so I printed out a copy of the course. Actually, printed out a copy of the course notes. We should just pause at this point in time and see if I can't make that a little bit clearer. So just, okay. So you'll see that when we started with this, we talked about functions always starts with definitions and a bit about the notation we're going to use for the course, what we mean by real value functions, inverse functions, trig functions, so techniques of integration, differential equations. So we notice we've got first order separable differential equations, growth models, Newton's law of cooling, Euler's method. So Euler's method is a numerical method for solving differential equations or finding a numerical solution. Then we've got all this stuff on vectors and parametric curves. Okay, so we can talk. That's why if you look over that list of revision seminars, there's a fair bit of stuff on vectors and the revisions in the previous revision seminars. System of equations, so defining what we mean by augmented matrix, row operations, system of 3-dimensional equations. There's the complex numbers. And what is the deductive reasoning? All right. So any of that stuff. Now, the other thing I did in preparation for this is I went back to when's this one from? So I have this. You'll notice is a sample exam. Now, I'm not sure if it's different from the sample exam that you've got in Maths1M at the moment. This is one I've had from a few years ago. I don't believe Maths1M has changed significantly in that time. And so what I could do is I could just spend some time talking about how you might talk about these particular questions. So do you guys have any feeling about what you'd like me to? So the other thing I could do is I could pick a particular topic, take differential equations, for example, and just sort of talk about what sort of you've seen in that and how you're expected to do that, and then maybe pick out the differential equation questions from the exam and talk about how that would work, talk about how you might go about answering that. There is sort of the general study skills about being prepared for an exam. So I'm going to pause for a moment and just ask, do we have any questions?
Yeah, could we go through the first order separable equations?
First order separable.
Yeah, thanks.
Sounds like a great plan. Okay. Right. Not loving this a lot. So you would have noticed that first order separable. So we're going to start. So whenever we start doing this, doing math stuff, we go, what's the definition? All right. And so, excuse me while why is that doing that to me? All right, sweet. Sorry about trying to turn the screen and turn the paper on you. I know it can make you feel a little bit unwell if you do that. All right. All right, so we use this thing where we go DEs. What I will do, I think I still have my notes up here because that will be the right way to do this. Outline 60, so I should be able to jump to. All right, what we're going to do is we're going to adjust. I know it's going to annoy. Where's this one? That one. All right. So here we've got what the course notes say. So differential equation, the general solution of a differential equation is a comprehensive formula which includes all the solutions of a differential equation. A particular solution is any one function which satisfies the differential equation. So that's what this is saying here. All right. So we're distinguishing between the general solution, which covers everything that we could expect to see as a solution, as opposed to a particular solution. We actually kind of like the idea of having a particular solution. All right. Because that can be really useful. So it can be sometimes easy to see a particular solution. And so you can sort of consider differential equation when you have something like that. So this differential equation here, all right, would actually be considered a separable differential equation. It's just that there's no y in that equation. So I'm going to just scroll down a little bit and see if, so see how we've said first order separable differential equations. And we've actually said that the derivative of y with respect to x is equal to, what did they say? Some function of x times a different function of y. All right. And further, they've gone on to say that the solution can be written as the integral of the one on the function of g, integral f of x dx. So literally, I'm separating the two things. Okay. So this is what we call the definition. All right. So what I'll do, so there's a few examples there. What I will try and do is I will try and find a different, what I might do is I might actually, so like I said, I've got this exam here. And so I'm going to have a pause momentarily to sort of have a quick look to see. So I'm going to have a quick look through my sample exam, see if there's a differential equation question. Because the differential equations that you would do for, that'll do. So the differential equations you would do for the exam would be different from the ones you would see in the assignments. One of the things I'm going to point out about this, right? See how this is quite a simple. So we're just going, maybe a bit hard for you guys to read, but consider the differential equation dy and dx is equal to x on y with initial condition y naught is equal to -1. All right. So they've allotted 4 marks for this, and just in terms of what that means, they have allotted 70 marks for the 120-minute exam. And so that means sort of you've got about 7 minutes to solve this problem, all right? Which, if we know what to do, should be a walk in the park. I'm going to spend a lot of time. I'm going to talk about it a lot, but so writing down the information. So question 3, sample exam. All right. So dy on dx is equal to x on y. And so we're going to put in that initial condition, or boundary condition, sometimes it's referred to. And so what we're trying to do is we're trying to match it with this form. All right. So remember, with every exam, we're going to have we're actually trying to give out information. We're trying to demonstrate that we've understood what was in the course notes. That's why I just thought we should just start with what's in the course notes. And so here, this is really simple. We've got f of x is just going to be equal to x, and g of y is just going to be equal to y. And so literally what I'm going to do is I'm going to separate. I'm going to put everything with an x over one side. Usually I put the x stuff to the right and the y stuff to the left, a bit like we've done in the solution. And so I'm timesing both sides through by y. So I'm going to have y dy, and I'm going to times both sides through by dx. So x dx. And then I just integrate. All right. So the integration here, nice and simple. Now, one of the tricks is normally I'd have a constant of integration and a constant of integration. Because if I had a plus c here and a plus c here, one of the first things I do is I put them together. I only need to add one constant. All right. And I could do things like multiply through by 2 here to get myself y squared is equal to x squared. And I'm going to go, because I haven't worked out what the c is, it's sort of algebraically, it's technically wrong. But in actual fact, it's the same thing when we're doing this. All right, we've actually got some arbitrary constant of integration. So we can definitely go through and do this. That's like the first step, right? If you think about this, this is like 2 marks of this thing. All right, this question is nice and easy. And so I could go to the next step and go y is equal to plus or minus square root of x squared plus c. All right. Sounds like a great plan. Then I've got this initial condition that I can put into this equation. So I'm saying when x is equal to 0, y is equal to -1. So -1 is equal to plus or minus square root. And so 0 plus c. So in actual fact, the only way this thing is going to be equal to a negative number is if I take the minus square root and minus square root of c. And so that's telling me that square root of c is going to be equal to 1. And so therefore c is equal to, actually it has to be equal to 1. I'm sort of squaring both sides to get me c is equal to 1. All right, so my solution, y is equal to minus square root of x squared plus 1. Okay. So when we come with differential equations, all right, so with separable differential equations, this one for the exam, reasonably simple. Okay. What we could end up with is, I'm going to try again with a slightly more complicated differential equations that I'm about to make up. Forgive me if this doesn't work out terribly well for me, because sometimes we'll have dy on dx, which is equal to sort of y e to the x plus y. All right. And so we actually have to do one step more of working out what's going to happen. All right. What we have to do is we actually have to go, all right, y is equal to e to the x plus 1. For exams, this is about as complicated as it will get you for a separable differential equation. And so I would then go, okay, I'm going to do that separation. I'm going to put my y over here. So I'm going to have 1 on y dy is equal to e to the x plus 1. And I'm going to put my dx. And then I'm going to slip in my integral side, integrate both sides. More complicated. This one, ln of absolute value of y is equal to integral of e to the x is conveniently e to the x. This is x, and this is 1. C. Okay, and so I've got my separable difference. I've separated my variables. I've done the step of integration. All right, and so if you think about it, like each line of working for the way from the sample exam is worth 1 mark of your time. All right, it's like worth basically more than a minute of your time, and so we can just do those steps relatively simply. I've got this unfortunate thing where I've got y is equal to. All right, and so ln of y is equal to. I don't really want that. What I would have to do is I'd have to go y is equal to e, and then it would have to be all of this, e to the x plus c. All right, and so notice this plus c in the power. This is where we go. This is like e to the c times by e to the e to the x times e to the x. All right. So you quite often see replace this bit by just going some number, which is horrible. But anyway, and so then I could take a value. So I could take an initial condition like y of 0 is equal to 3. When I put in 0 into here, I'm going to say 3e. So what we're saying is we've got 3e here is equal to a times e to the 0 times e to the 0. E to the 0 is equal to 1. We know that one. And so this is like a times e to the power 1 times 1. E. This is just e. And so a is equal to 3. Whoops. And so therefore my y is equal to 3 e to the x times e to the x. So I can actually little bit of messy stuff, but we just need to know we just need to be confident about what we're doing, and it will come together. Okay, did we follow that? Yes, sweet. Okay, now what I'm going to do, I'm just going to swap back to the lecture notes and just see if there was anything in particular that they talked about. All right, so they gave us some examples. So you see that first example here, that is sort of going, all right, there's nothing really very important going on there. This one, there is a degree of separation that's got to happen. And this one, so here there was a function of u, but not actually a function of t. Here there's both functions of x and y. This third one, there's only the function of y, not a function of x. So when we have that thing where there's not actually a function of x, so if I just to sort of explain that, so dy on dx is equal to e to the 2y. I'm sort of going, I'm going to times by 1. All right. So what I have to do is I have to go that one. I have to sort of, so if I write out the differential equation, if I then times by 1, that means I can separate this. So I can do the 1 on e to the 2y dy is equal to 1 times dx. All right. I don't want to just pull this over here. This is effectively allowing me to sort of, this is relatively simple, right? Possibly when I'm doing this, I'm going to write this as 2y, so minus 2y, just to make it so I can just integrate that. And over this side, I'm going to go x plus c. I'm actually just going to do that integral, and I'm going to put the constant of integration. When I'm doing this, like if I got really pedantic, right? If I got really uptight about this, I'd go let u is equal to minus 2y, and so du dy is equal to minus 2. And so I'd go, and so that would go dy would be equal to minus 1 on 2 du, and so my integral becomes minus 1 on 2 e to the u du, which is minus 1 on 2 e to the u, minus 1 on 2 e to the minus 2y. You kind of know that anyway. That's the thing you would have done anyway. But and so we could go through and unpack that. So we could actually go e to the 2y is equal to what's that, minus 2x. If I'm just timesing by a constant, I haven't worked out what this c is, so I can get away with doing that. But you noticed last time what I did, so I took ln of both. If I take ln of both sides, this would be like 2y is equal to ln of minus 2x plus c. The c has to be inside the brackets. All right, so this c has to be inside the brackets to get that working correctly. Okay, so are we okay with how that works? Okay, what I'm going to do, I'm going to go back to the lecture notes and just sort of see if they've mentioned anything else. Okay. So population growth. So they've basically introduced separable Ds, and then we've gone to what's this? Talking about population. A simple model for population growth is assume that population growth rate is proportional to the current population. This can be written in the form blah. So derivative of p with respect to time is equal to some constant multiple of the current population. In some population that is varying with time, and k is a constant which represents the growth rate. This is a first order separable differential equation with a solution of the form p is equal to a e to the kt. All right. So you can see how they've given you some examples of that simple population growth model. Okay. And so then your example, suppose that a lake contains 100 fish. 1 year later, there are 120 fish, assuming an exponential growth model. This is then fitting that growth model to the information you have. Okay. So we could go through, let's have a look. That would be a way. So if I was to do that, all right. So this is the same sort of process that you might go through with this sort of thing. So you might actually start off with your population is e to the kt. All right. And so if I know, if I have 2 points, so if I have p of 0 is equal to, say, 200, and p of, say, 3 is equal to, let's try something simple like 400. All right. Because I know these 2 points belong to the equation, I can go that's a e to the k times 0. And this is equal to a e to the k times 3. Whoops, I'm going to change this back so that I can talk about where to go. All right. I bumped that again. Okay. So I've arbitrarily chosen, I'm supposing we've got this data here about this model. So we're told it's a growth model. We're told this particular piece of information about it. And so this is A times e to the power 0, which is just A. So we're allowed to just go A is equal to 200. So quite often you'll see us give you P of 0 or the initial population. All right. And so that when I go, all right, so my 400 is equal to A e to the, I'm going to say 3K, which is equal to 200 e to the 3K, right? Because I now know what A is. I can then go, all right, I'm now in a position to solve this, all right? So hopefully this solving part is relatively simple from here. 400 on 200. Cancel out my zeros. This number is going to be 2. So I'm going to take natural log of both sides. And so 3K is equal to ln of 2. And so K is equal to ln of 2 on 3. Sometimes when I'm actually doing this for an actual question, I won't actually work out what this number is. I'll leave it as ln of 2 on 3, because in this equation here, it's going to be more accurate, all right? So my population model, my population as a function of time would be equal to 200 e to the ln of 2 on 3 times t. So yeah, okay. Oops, there we go. All right. So do we have any questions so far? Like we lost our other people here for a second, quite quickly. All right. Okay. So what I'm going to do, if I look back at this sample exam, what I'm going to point out is they asked this question about using method of different separate. Well, this differential equation, which we observe is separable. They said solve it explicitly. They said use Euler's method to estimate y1. Okay, so what I'm going to do is I'm going to talk a bit about Euler's method, because basically the reason I'm going there is because it was like the next part of the question, and so that's what made me think, oh well, maybe there's something about them putting that straight onto the back of the next question. So maybe what I might do, so what I might do as a bit of an exercise in working out what this is, Euler's method 66. I'm actually going to go back to the lecture notes. And so we're nearly at the bit where they talk about Euler's method. Newton's law of cooling, Euler's method. So the first thing we're going to know is that with Euler's method, this is when we go, we can't actually solve it. So the question in from that sample exam, we actually had an idea of what the actual solution might look like. But with this sort of when we come to more complicated differential equations, we may not be able to do this, all right? So we might have a differential equation. So I might have a differential equation, which I can't separate. You can't write as a separable differential equation easily. And so I might then go, well, what I'm going to do is I'm going to do this first order approximation. Okay, so I'm going to do this thing where I go, see how we go to approximate. In the notes here, it says to approximate y of a plus h, we take y of a plus h times y dashed of a. So basically the slope. So this is what we're doing. We're going, if we come down to the diagram here, you can see we've got some point. To get to the next point of approximation, we're going to go across some h step, and we're going to follow that along the slope. All right. And so we can keep doing this. All right. And you can see by our little diagram as we go forward, we're going to keep trying to make approximations. Okay. I'm going to have a bit of a scan of the lecture notes. So one of the things about Euler's method is we're gonna take a discrete number of steps. All right, so we're going to decide that how big my horizontal step is, and we're going to fix that so that we can work out an approximation. So I'm going to swap to my sheet where I've written out myself an example. All right, so I've got a differential equation with an initial condition. Now, what I'm going to do, so I've picked something that is not easily separable, right? I can't just solve that. I have a few ideas about what I could do to solve that, but that's a different story. We'll worry about that another day. What I am going to do is I'm going to go, well, let's say I want to find, I'm actually going to do something which they wouldn't do in the exam. I'm going to try find y of 2 with h is equal to 0.5. All right. So I'm going to take 4 steps. All right. So what I'm going to do is I'm going to set up a table of values. All right. I'm going to have my x values. I'm going to have my y values. I'm going to have my dy on dx. And sometimes people put in h times dy on dx. All right. So my h, what's going to happen with my x? So that's going to start at 0. And I'm going to plus h each time. So 0.5, 1, and so we've got this thing where your x of sort of k plus 1 is equal to x of k plus h. I'm always adding a little bit to that, to the x value, the same amount at every step. With my y value, so we go y of k plus 1 is equal to y of k plus h times dy on dx. This we evaluate at that point. So what we're going to do, my y value I said started at 1. My derivative at this point, so I'm going to put in x is equal to 0. This corresponds to the point 0, 1. And so x is equal to 0, y is equal to that. And so I'm getting minus 1. Okay, sweet, minus 1. Everybody's happy with that. Now, so when I come here, this is like the change in y. This is what that value is here. So I'm actually going to work out what that number is by just going this number times by my h. Minus 1 times by 0.5. Okay, so my x I added h to, my y. Just 2 seconds. What's up, guys? No, that's okay. All right. All right. this number minus 0.5. So if I go y, so this is going to be 1 plus minus 0.5, which is going to be just 0.5. So all right. So now I've got a new point. This actually corresponds to the point sort of 0.5, 0.5. Okay, so I've got new values to put into my derivative function, which is going to be a little bit, so 0.5 squared, I'm going to write that as a quarter plus, this is going to work out to be a quarter. And this thing here is going to work out to be minus a quarter. All right. That works out to be a quarter. That's interesting. All right, cool. Bit of fun. Wasn't really expecting that, but then again, didn't think too much about what I was expecting. So when I come down to this bit here, this is like a quarter times by a half. H is a half. And so I've got 1 on 8. All right, 1 on 8. Cool. Everybody happy with that. When I come down to this, I've got a half plus 1 on 8, which is going to be 5 on 8. And now, so this is my new y value. This is my new point. So my new x value is 1. My new y value is 5 on 8. And so when I come to work out this one, so it's going to be 1 plus, so this is going to work out to be 5 on 8. This number here, so we're going to take away, that's going to be like 25 on 64. This is a horrible number on 64. Let's think about this. This is going to be 40, so that's going to be 15. So plus 15, 64 plus 15 is 79. All right, sweet, woohoo. And so I've got my 79 on 64. And so I'm going to times that by a half. And so I've got 79 on 128. Horrible number. I might stop it. What I might do is I might stop here because at this point in time, it's getting ridiculous. But I've added h again. I'm going to add this and this together. All right. So I'm going to add my previous y value to my change in y value. And so that is going to be something like 128. So I had to times by 16. So 16 by that is going to be 80. And so this is going to be 159 on 128. And so I have a new point. I have 1.5 and 159 on 128. All right. I think at this point in time, I've kind of got to the point where me doing it by hand is going to be difficult. All right. Just to sort of quickly try and plot this out. All right. So what I had here, so we were at this point here, we actually went down. I'm going to print, this is 1, so this is a half, and this is 3 on 2. So we went down to this point here, then we went, so this is only just ever so slightly up from this point. All right, so I can make, and then when we come here, this number is about, what would that be? Okay. So 1.5, this is actually coming up to about, I'm going to say 1.5 for the purposes of this discussion. It's about more like 1 1/4 or 1 1/3. But we've got this sort of nice sort of, you can actually start seeing this thing starting to take shape. All right. And so we could actually do this through these points here. All right. I won't try and work out what the actual function is. And I might stop it at that point there. Okay. This is the point where I go, okay, so through hiccups and stuff, we've managed to get to a point where we've actually covered some topics which might be interesting. Do you have questions? Okay. What I'm going to do, I'm going to click stop sharing for a second. And so I wonder if I can do this. What I'm going to do is this recording. Okay, so when we're talking about things like this example 2.2, 4.2.2 here, suppose you start at a point in space and you head in a direction of head a distance of 3 units in the direction of, in this case, we've got a nice vector that's already length 1. All right, what I might do is I might try and sort of simplify it a little bit to then sort of make it more complicated, if that makes sense. What I might do is I might try and talk about an example about what you would do if this was in 2 dimensions, but we didn't have a nice vector. So the initial thing you said was actually about unit vectors, right? And it's kind of like a unit vector is just a vector of length 1, okay? So what we'll do is we'll get you to stop sharing your screen at that point in time. All right. So, okay. So first thing to go. All right. That is all a unit vector is, right? Unit vectors are really useful though, because if you saw in that dot product formula, if I have like u dot v, it's equal to length of u times length of v times cosine of the angle between them. If I want to know something about u, but I don't like the angle between them, all right, it would help if these lengths are not a factor in that calculation. And so that's why having a unit length would make my life easier. The other thing we say, I know we say this, right? So we actually go the length of a vector k times v, where v is my vector, is equal to k times the length of v. Possibly we should say absolute value of k, because it's just if k was a length. And so like when I've read that, I thought that's really, really useful. I'm not sure why they're telling me that. Doesn't help me at all. But what that means is if I do v divided by the length of v, all right, then the length of that vector is going to be equal to, this is, if I write this as 1 on the length of v times by v, this number here is just a constant. So it's like the absolute value of 1 on the length of v times by the length of v. So hang on, length of v and length of v, they're going to cancel each other out and they're going to be 1. And so this is a way of calculating a vector of length 1. So we actually do this to calculate unit vectors, all right? And unit vectors, like I say, possibly one of the more important concepts in mathematics. Not so much in that it's complicated, all right? In fact, it's actually really simple. I'm just talking about a vector of length 1. But it makes doing so many other things better, simpler, all right? So, for example, the example you were talking about there was just simply taking a point. So start at, I don't know, 1, 2, 3. All right. And travel 4 units in the direction, I don't know, 7 minus 2, 5. All right. Arbitrary numbers. Hate to say this, just pulled numbers out of nowhere, decided they seemed like a good idea. Okay. This vector, so what I need to do, because I want to travel 4 units in that direction, what would make my life easier if I turned that into a unit vector? So I'm going to go my start point. So I'm going to P is equal to 1, 2, 3. And what I want to do is I want to go plus 4 times a unit vector in that right direction, in that direction. So I'm going to go u is equal to 7 minus 2, 5, divided by the length of the vector 7 minus 2, 5. All right. So I'm going to turn this into a unit vector. All right. So I'm doing that because then to go 4 units in that direction is just 4 times that vector. All right. So my bit on the top didn't change at all. This is square root of 7 squared plus minus 2 squared plus 5 squared, which is 7 minus 2, 5 on, and so square root, this is 49 plus 4 plus 25. So 29 and 49 would be 78. That's a horrible number. 1 on square root of 78 times by 7 minus 2, 5. And so to actually work out where I'd be after this, I'd go, my point would be 1, 2, 3 plus 4 on square root of 78 by 7 minus 2, 5. If I want to get a little bit clearer, so that should be 28 on square root of 78 minus 8 on square root of 78 and 20 on square root of 78. And so my result, feel free to tell me that I've dropped off the bottom of the page, would be 1 plus 28 on square root of 78, 2 minus 8 on square root of 78, plus, and then 3 plus 20 on square root of 78. That's all it is. So by creating the unit vector and going so many units in that direction, I can actually just do this as a vector equation. All right. So that actually keeps that relatively simple. So that I can actually work this thing out. All right. Did that actually explain what you were hoping to see?
Yeah, that helped. Thanks.
Next on the list. Is there anything, anyone else got questions? Because there's things like projection. So projection is actually where the first place where we use unit vectors quite a bit. All right, that being able to do the projection of equations, or projection of a vector onto another vector. I tend to like to talk about it as the shadow of the vector on the other vector. The point about it is the thing I'm projecting, I don't want the factor of that length of the vector I'm projecting onto to matter. All right, so that's why I project onto a unit vector. If you actually look at the formula, so projection of u onto v would be equal to, so we do u dot v times by v all on the length of v squared. Now if we unpack this formula just a little bit, this thing here going to be length of u times length of v, and this thing is going to have a factor of the length of v. And so what I'm doing here is I'm effectively cancelling out the length of v, because I don't want the thing I'm projecting onto I don't want my projection to change based on the length of the thing I'm projecting onto. All right. So if you imagine, like, I don't know, the shadow of a goalpost on the ground, you don't want the shadow doesn't depend on how much ground it is, does it? The shadow is still the shadow, regardless of how much ground I have to project onto. All right. So I don't want that to be a factor in my calculation, which is why I've taken by dividing by that length squared, I'm removing that factor in that calculation. Projection. This thing is always in the direction of V. So when we're doing this, my projection, if you look at the formula, this part here is just a scalar. It's just some multiple, and so it's some multiple of that direction. And that's why ideally we want to start with the length of the vector V as being 1, so that we don't have, because we only got V there because we want the direction that V is going in. Okay. Do we have more that we can talk about?
Hi, Nick. Are you able to do an example question of a mathematical induction?
Yes, I can do a mathematical induction. Love mathematical induction. What I might do, having a bit of a think off the top of my head, can always be a bit of a problem. So I'm going to have a quick flick through to see if I can find something that would be a suitable question. I need to yes. Wonder, because there's all sorts of things we could do with this. Oh, they love that one. All right. Okay. All right. So let's go do this. That one. Okay. Not sure how well you can read this, but we've got use mathematical induction to prove that n squared is greater than m plus 1 for n greater than or equal to 2. Okay. I feel like that is a plan. All right. So prove n squared greater than n plus 1 for n greater than or equal to 2. Okay. So we're going to proposition Pn, n squared greater than n plus 1. So when we talk about a proposition is something with a true or false value, right? So it's just a statement. In this case, it's a mathematical statement. It is either true or false. This, depending on what value of n takes, it is either true or false. So there's very few n where it's not false, not where it's false. So if I took n is equal to 0, that would be false. If I took n is equal to 1, that would also be false. So after that, pretty much always true. But anyway, one of the other things, there's a specific part about the way you think about these things, so that we can actually so we can actually do these calculations when we're doing inequalities, all right? So, so P of 2. So the 2 is my initial case. All right. That is 2 squared greater than or equal to 2 plus 1. This is 4 is greater than or equal to 3. It's true. So P of 2 is true. All right, loving the plan. Okay. Now, we're going to consider P of K. And so I don't want greater than or equal to, really. I just want greater than for this question, don't I? Yep, beautiful. Okay, let's consider this. K plus 1 squared. K plus 1 squared is like K squared plus 2K plus 1. So I'm going to take this. All right, I'm going to take 2K plus 1, this bit, and add it to both sides of this. So I'm going to have K squared plus 2K plus 1 is greater than K plus 1 plus 2K plus 1. Now, I assumed this was true. We should have said and. That we should have said that we're assuming this to be true. So we're assuming this to be true. We started with something true. We added the same thing to both sides. We still think this is true. We're going to write this as K plus 1 whole squared. Of course, we've already seen that that's the same thing. All right. Now, so I'm actually going to go K. I'm going to put the plus 2 plus 2K. Now, if K greater than 0, all right, my 2K would be greater than 0. And so I can actually do this thing where I go K plus 1 squared is greater than K plus 2. And I'm just going to set that to be 0. So what I did is I replaced this with something that's smaller than it. So I preserved the inequality. All right. So I did this thing where I assumed PK to be true. And I've shown that PK plus 1 must follow. All right. So I've actually shown that inductive step. If PK is true, then P of K plus 1 is true. All right. So it's allowing me to go, hey, this is my inductive hypothesis. This is my inductive step. All right. And so we can then go, since P2 is true and PK plus 1 is true if PK is true, K greater than or equal to 2, then Pn is true for n greater than or equal to 2. All right. We should go by principle of mathematical induction. All right. So we're actually using that principle of mathematical induction to go, hey, I've shown my inductive step, I've shown my initial case, I can claim this thing is true. And if you really want, you can go, that is n squared is greater than 2, so greater than n plus 1, or all n greater than or equal to 2. So it can actually, yes.
Yeah, sorry. I've kind of lost you a little bit when you added 2k plus 1 to both sides. Like, why would you?
Why would I do that? So what I actually did to work, like, I'm thinking about what the next step would be, all right? So implicitly in here, I've gone P of k plus 1 would be k plus 1 squared greater than k plus 1 plus 1. K plus 2. So what I wanted to do is I wanted to get to that bit. So I had
Yeah.
I wanted to go from here to here. And so I kind of expanded it out and gone, oh, the difference between k squared and k plus 1 squared is this 2k plus 1. I know it's, so that's that thing where what I do is I do a look ahead from this point here. I've assumed this to be true. I look to see where I want to go. Okay.
I see. So, and you kind of not quite worked backwards, but you bridged that.
Bridge that gap.
Yep.
Yep.
Yeah, I see.
So, so that's an example of an induction. Inequality ones, this idea where I go, hey, I'm just going to take away the 2k, because if without that, that's the thing that I'm interested in. And that's just making my number smaller, so it's preserving the inequality. That idea actually breaks some people's mind. They're like, why would I do that? I could say, the answer is, because it's going to allow us to say exactly what the statement is. We want it to be very clear, this thing must be less than this thing. If I take away a little bit so that it looks exactly the same, I'm still keeping it less than, so it must be true. Would you like me to try another induction example?
That would be good. I would. I don't know if the others want to.
Yeah, that would be great.
Okay, so there is some funky formula. All right. And so so if I go summation, I think you guys have done summation, haven't you? Have you done summation stuff where I do I is equal to 1 to n, and if I do I squared, and so that's equal to n plus 1 to n plus 1 on 6. So you have seen the summation. This is where I go, did I remember that was in there somewhere? I'm sure it was.
I've seen the summation sign, but we haven't done it in Maths1M. So
Haven't we?
I don't think we have.
So you did upper and lower sums. Now looking at it, I'm going, oh, you didn't. You don't have the upper and lower sum things in here. And so I'm like, all right.
No, yeah.
What I'm going to do is I'm going to try and do this 1 plus 2 plus 3 plus ... plus 1 squared plus 2 squared plus 3 squared plus n squared is equal to n plus 1. It's just a notation, so I can get it right. I get around. Let's do that. See, this is the problem with what I do is I will go from talking about Maths1M to Maths1A to Maths1B to second year maths and a whole pile of other things, and I forget what's in what course. So, and I think I'm getting confused between 1M and AQMF, so application of quantitative methods in finance. So the process is still the same, all right? So what I'm going to do, this actually applies for n greater than or equal to 1. All right, so my Pn is equal to, is the proposition 1 squared plus 2 squared plus 3 squared plus ... plus n squared is equal to n plus 1 to n plus 1 on 6. So my proposition for 1 is going to be 1 squared is equal to 1 times 1 plus 1 times 2 times 1 plus 1 on 6. This is going to be 1 times 2 times 3 on 6, which is equal to 1. P1 is true. All right. Okay, so now we're going to go assume PK is true. And then we go, that is 1 squared plus 2 squared plus 3 squared plus ... So there's a lot of writing out with these things where you've just got to go, oh, this is what I've got to do. I will just embrace the writing it out. And I've seen, I had one student I tutored a long time ago now, and she just did the writing out and she got through stuff very quickly. She didn't really understand a lot of what she did, but she got through it very quickly. So she almost always finished her exams early. She didn't do very well, but she did finish early and she did pass because the things she knew she could do quickly. What I'm going to do, this might sound like a crazy thing. So now add k plus 1 squared to both sides. This is just adding the next thing to this side. So I've got 1 squared plus 2 squared plus 3 squared plus ... plus k squared plus k plus 1 squared is equal to k plus 1, 2k plus 1 on 6 plus k plus 1 whole squared. This is the right thing. So I'm just going to focus on this side here, okay? And I'm going to do a thing where I take k plus 1 out the front. And so what I'm left with is going to be k and 2k plus 1. If I put it all on 6, I've got to times by 6 on 6 here. So this is going to be plus 6 times k plus 1. I've taken one of these k plus 1s out as a common factor. So a k plus 1 from here and here. This is actually to make my life a lot easier in a second. So all I'm going to do is I'm going to expand and simplify that numerator. So I'm going to have my k plus 1, and then I'm going to have 2k squared plus k plus 6k plus 6. All right, I feel like that's a thing on 6. Okay, awesome. Everybody happy? And so k plus 1. So I tend to refer to this as messy algebra because it's just a matter of being careful about your factorization and your algebra at this point in time. I ideally want to take this bit here and write this as, I reckon it should be, well, it should be 2k and it should be a k. And those two numbers should get me a 6. And so everything's positive. These numbers should be plus. So if I have a 3 and a 2, if I put my 2 here and my 3 here, I'm going to get 3k and I'm going to get plus 4k. That's going to get me 7k, 6k. That's actually the factorization of that top line. Woohoo. So I'm going to write that factorization in. So I can now write this as k plus 1. I'm going to go k plus 2. And then this is 2k plus 3 on 6. I'm going to rewrite that ever so slightly. K plus 1, k plus 2, and this is 2k plus 1 plus 1. But hey, this implies pk plus 1 is true if pk is true. Did we love that? See how this would be if I was to put in if I go back up to the top here, and if I replace that by k plus 1, maybe what I'll do, so if I just to sort of put it down the bottom here, so if I had k plus 1, and then k plus 1 from my original statement, and then 2k plus 1, that's going to be the same thing. All right, so this bit here is just saying that that's actually what it should be for pk plus 1. All right, and so we can go by principle of mathematical induction. Since P1 is true, and if PK is true, then it's kind of tedious, this bit. PK plus 1 is true. Pn true for all n greater than or equal to 1. Oops, damn. All right, so this bit here is where I finish it off. This is me saying I did all the bits that I needed to do, and so I can say that I've proven the thing I've done. All right, it's really important that I get into the habit of saying I proved what I said I was going to prove. All right, and so the other part about this is, I mean, like, I've done this particular one more times than I can remember, which is, you know, only sort of somewhere in between 20 and 50 times. But the first time I did this, I didn't know what was going to happen. But I did know that if I start with pk and I add the next term to both sides, I was pretty confident that when I simplified this down, I was going to get what I needed for pk plus 1. All right, so I knew that if I started with the thing I assumed to be true and I added the same thing to both sides, then I can get to the thing. So that's the sort of thing when we look at what we've got. So there's multiplicative inductions, there's additive or summation inductions like these ones, there's that inequality inductions, and each of them has a slightly different thing that you want to be doing, but it's always about starting at some point and then going, what do I have to do to get to the net point? Let's try and do that thing so that at least one side is exactly what I want, and then hopefully the other side will become what I need to. So in the inequality, I've just gone, oh, I'm gonna sort of go to the next value, but then I have to make some changes about what it's going to look like to get to the actual value of what the actual thing that I'm looking for. So yeah. Did we follow what I was saying there, people? All right, this is a good point to pause again to just check that you guys are all good, see if we've got more questions, or if you've sort of had enough and want to sort of move on with the next part of your day. So what I'm going to do is I'm going to stop sharing. And so if I go here, okay. So the next thing we're going to do is talk about a bit about polar form for complex numbers. We understand we can actually do this with any point in like R2. We can actually give it a polar form, right? We could actually write it as a length and an angle from the positive x-axis. For complex numbers, it has some additional properties, all right? So what I might do is I might just pause momentarily and go, so if we have my complex number a plus bi, that has a polar form, which would be r cis theta. That's actually a shorthand for saying r times cosine theta plus I sine of theta. Whoops. All right, this works a lot better if I actually share the thing that I'm writing down. Feel free to tell me I'm doing something silly like failing to write down the, failing to switch the camera to what I'm doing. All right, so this is just a shorthand. All right, and so if I was to sort of do my little graph of the Cartesian plane, and I've got my point out here, this is like a plus BI. So down here is A and across here is B. This angle here is theta, okay? And so if I think about that triangle, all right, I could actually go, so if I go like tan of theta, that could be like B on A. Or if I like the imaginary part, on the real part. This is only actually going to be true if I'm in that first quadrant. In actual fact, it kind of still works if I'm down here, because the sign of this bit will carry through, make my angle negative, and so that will work, but it won't work over here. So one of the first things we need to do is recognize that when calculating the argument, we have to be aware that there may be some induction, some adjustment to the argument that's needed. So so that's sort of the thing where we're going with. And so yeah, so we'll just we'll go with this plan. Okay, so we've got our argument, we've got these things. One of the beautiful things is we have de Moivre's theorem. All right, so there is finding this thing, and then there's properties. Okay, so if I have like a Z1, which is equal to R1 cis R1 cis theta 1, and a Z2 is equal to R1 cis theta 2, then if I do Z1, what happened? Why did my camera decide to stop working? Oh, okay, we're back. Sorry about that. That happens from time to time. R2, Z2. So if I do Z1 times Z2, there's this cool thing that happens. I won't go into it. Hopefully you did in your lectures. Cis of theta 1 plus theta 2. Okay. So right. It's a thing. We're happy about it. So we can see that the length is just the product of the lengths, and the angle is just the sum of the angle. And you can actually, this actually follows when we do various other properties. All right. So this is like R1 on R2 cis of theta 1 minus theta 2. So the lengths do the same thing as the complex numbers. The arguments, rather than they act like the power. All right. And there's more to that, and I won't go into that. That's something you'll talk about later on if you do more mathematics. But we've got this cool thing happening. And so specifically, if I have Z1 to the power n, it's going to be R1 to the power n cis n theta. Okay. So we've got these things. These are the things that are going to make my life easy. All right. So they're the things that I want to be focusing on, and they're the reasons I would choose to do this. So a way to think about this is if I take something like a quadratic, I have like a general form, and the general form is really useful for me to just get a bit of an idea of what the quadratic is, right? It's got that leading coefficient. You can sort of tell how stretched it is. It's got a constant coefficient, which is going to tell me what the y-intercept is. And there's nothing too complicated about it. Whereas I could have a factored form of a quadratic, and that's going to highlight what the roots are of my quadratic. And so my point is that different forms highlight different features of this thing. So with my complex numbers, you might go, oh, this is really good. It tells me exactly where it is. This is another way of telling me exactly where it is. So I go up some angle, I go out some r, and so I can actually work out what these things are. All right. but I might need to, so it depends on what I'm going to do, all right? So when I'm doing multiplication and powers of complex numbers, actually looks like the right thing might be that my polar form works out easier than my Cartesian, my Cartesian form, my sort of a plus bi form. And so so the reason I would use polar form is the calculation that I'm wanting to use with these complex numbers might become easier with that thing. So there is a lot of standard complex numbers. If I go Z1 is equal to -1 minus I, all right. So length of Z1, that's the standard sort of, 1 squared plus 1 squared is equal to square root of 2, square root of 2. And so my R1 would be square root of 2. And so if I actually draw this on the thing though, -1 down here. All right, so I can either go, my argument goes this way, or my argument could go this way. Depends on which one I want to do. So, if I was to do my tan of theta is equal to my imaginary bit, which was -1. So when I talk about the imaginary part, I don't include the I, just the coefficient of the I, and my real part, and so this would be 1. And so if I do arctan of both sides, that would be saying theta is equal to pi on 4. Pi on 4 is out here. This angle is clearly not pi on 4. So what I have to do is I have to adjust it, all right? And so for tan, the appropriate adjustment would be to add pi. So I could write this as 5 pi on 4. In actual fact, possibly, whoops. Oh, we're going to pause momentarily while I remember to plug the power into the laptop, because I keep forgetting to do that because I'm not plugged into my desk. Okay, that one. Okay, sweet. Okay, front facing camera. No, we don't want that. There we go. Beautiful. Don't know why it decides to do that, but every so often. I could have also done pi on 4 minus pi. All right, so you can see the 5 pi on 4 is going around sort of anti-clockwise. This would have get me -3 pi on 4, and this one is the principal argument. All right. Okie dokie, Joe. This thing. But and so with this, we want to understand that the principal argument is sort of either go negative to this point or positive to this point, but we don't want to have our argument crossing over the sort of the negative part of the real axis. And so that's how we can do this. So this one is one of those standard ones where we've got a nice argument, all right? And we like to keep it to those sort of things where, so we had, I don't know, I'm going to go 1 minus, how about we go 2 minus 2 root 3i. All right, so again, little sketch. All right, 2 minus 2 root 3i is down here. And so this time, we could work out what this thing is. So let's do the length of Z2, which I'm going to call R2. which is equal to square root of 2 squared plus minus 2 root 3 squared, which will be square root of 4 plus, so I'm going to be 4 times 3. Square root of 16, which is equal to 4. Woo! All right, nice happy number. I'm choosing very specific ones because they have nice answers. If I do my tan theta is equal to my imaginary part, minus 2 root 3 on 2, that's actually going to tell me that theta is equal to minus pi on 3. All right. If I shoved it into my calculator, it would have told me that. That's actually the right argument. All right. So I can do that. Another thing we could have done, though, is I could have done, so if I thought about this, I could have done cosine of theta. So when we do cosine, it's like is equal to the adjacent, which is like the real part on the length. All right. And so in this case, that would have been 2 on 4. If I do, so if I do that, see if this is a positive number, that would have told me that theta would have been pi on 3. All right. Sort of out here. So there's special rules. Whoops. There are special rules to convert between. So if I use tan, the answer is I add pi or take pi, depending on what the right value is, because pi is the period of the tan function. For cosine, the identity is cosine of theta is equal to cosine of minus theta. So we're saying this thing is an equivalent value. All right. I just need the other theta, the other angle that gives it to me. And so in this case, your theta 2 would be minus pi on 3, same as we got from the tan. So we use the diagram to tell us which thing we're supposed to be doing. All right. So I'm going to go, that's page 8. And so the thing I liked, so there are 3 things we remember. Okay. So there's tan of theta is equal to tan of theta plus any number of any integer multiple of pi. All right, so I can add or subtract a pi to get to the value I want. We've said cosine of theta is equal to cosine of minus theta. All right, so basically I just changed the sign on it. If the thing I got out of my formula isn't the right value, then I change the sign on it. And sine is possibly the most complicated one of them because it's sine of pi minus theta. All right. And so I've got, so if the value, so if I got sine is equal to pi on 3 and it wasn't the right value, then I would do pi minus pi on 3 and I would get 2 pi on 3. And that would be the value. This is not obviously the case in this particular situation. So we get to know which quadrant we're in, which will tell us which is the right value, which is the right formula to use. So in terms of the quadrants, my tangent works in the first quadrant and the fourth quadrant. My cosine works in the first and the second quadrant, and sine is the same as tan and works in the first and third quadrant. You notice there's no rule that works in the fourth quadrant. Okay, and so sorry, the third quadrant down here. That means that if my value is over here, I have to do something with it. All right. Personally, I suggest you just use the tan formula because that's going to be the one that gives it to you most easily. Since we're talking about polar form, and we've got sort of things going. So what I would actually do, my favorite thing to do is if we go z is equal to, if I just go cosine theta plus I sine theta, then z squared should be equal to cis of 2 theta. All right. this is by the de Moivre theorem, which would be cosine of 2 theta plus I sine of 2 theta. But I could actually do this, couldn't I? If I do cosine of theta plus I sine of theta times by cosine of theta plus I sine of theta, and then I expand that out. So cosine times cosine going to be cosine squared theta plus I times sine of theta cosine of theta plus I cosine of theta times sine of theta plus I sine theta squared. That's going to get me I squared sine squared. So this is actually going to be cosine squared theta minus sine squared theta. That's a real part and that's a real part. So I'm putting it together. And then I'm going to go plus I sine theta cos theta. This is actually sine theta cos theta. So it's like 2 sine theta cos theta. Okay. If I now equate real and imaginary parts. So I'm going to have this is equal to this. So cosine of 2 theta is equal to cos squared theta minus sine squared theta. And sine 2 theta is equal to, sine 2 theta is the imaginary part, so it's this bit. 2 sine theta cos theta. Do we love this? This is actually how I learnt to remember these formula. And so I could do a thing where I did sort of, a Z1 times Z2 to get me my addition formula by doing Z1 times Z2. I could get the addition formula for like theta 1 plus theta 2. Okay. So did we cover the stuff about complex numbers and polar form that you wanted to hear about?
Yeah.
All right. So how are we feeling about this now? What I might do is I might stop sharing and then I'll just pause this through is go, okay, so after a brief pause, we're sort of going to say, I think we've had all the questions that we want. Remember, there is a lot of these seminars that are already online. So we've got lots of topics covered on the Math Learning Centre resource page for Maths1M. You can come and visit us in the Math Learning Centre, and you're welcome to come and talk to us up until the exam. I don't know when your exam is, so I won't try and tell you anything about the exam except for to go good luck with it. From the point of view of so if you need help, remember Maths Learning Centre is online. Remember, this is my advice. I am not part of the School of Maths. There are things that you may have done in the course that I may have done slightly differently here. And that is, so I've tried to do my best to match what I think you will have done in the course. But, and I know mathematically speaking, what I've said to you is correct, but I may make mistakes when I'm working. So when I'm presenting, I quite often will make minor mistakes in my algebra or in calculations. So please don't take them to heart. You follow the idea, make sure you correct it as you go for yourself, not trusting like if you reproduce something I've done here in the exam, make sure you do the algebra or the calculations correctly. This video will go up online in the resource page like all the other ones. And so good luck with the exams. Hope to see you guys in the drop-in centre when you have time, or not. Good luck coming, and maybe next semester when you're doing Maths1A. Thanks, guys.
Yeah. Thank you.
No worries. Reach. All right.